Move to lecture 4, diffusion mechanism. So just give you some quick review about the lecture 3. What did we learn from lecture 3? You formulate the diffusion equation and try to do what? Then try to no matter it's under steady or non-steady state, you try to solve this diffusion equation and to get how the concentration of diffusing atoms change with location and time, right? So for example, if what we have here is we have a little bit ugly, but we have a secant substrate here, and then we have we deposit limited a very thin layer of diffusing atoms on the top of this secant substrate and allow diffusion happens. So as you remember, the solution for this the concentration profile of this the concentration profile of this diffusing atom probably will be shown like at T1 and probably at T2 will be like this, right? Because it belongs to limited case, right? But in lecture 3, we don't have chance to, you only know the concentration distribution inside our materials after diffusion happens. But so this is, we can call it as a macro scale point of view. You can observe the concentration profile of diffusing atoms, but you don't know what you don't know. You don't know how the diffusing atoms, for example, like I changed the color. You have no idea how the diffusing atoms, moved to arrive to how the diffusing atoms really moves through these materials during diffusion. So this is what we are interested in and want to show you in this lecture. Is related to the diffusion mechanism to describe in micro scale how the atoms diffuse into these materials. And based on this, we also will know show you how to estimate the diffusivity of these materials and also the relationship between the diffusivity, which you can measure in a macro scale, and atomic movement or atomic diffusion in crystals, which you observe in micro scale. Okay, so let's take a look on our outline. So in lecture 4, we can simply separate into two parts. The first part we call is a thermally activated diffusion. Thermally activated diffusion means what? Means that the atoms only have the energies only come from the thermal energy, kT. And in this part, we are going to show you what is the atomic jumping process in your materials. And also introduce you the random walk and also the correlated atomic jumping process. What are the difference between the random walk and correlated atomic jumping process? So you have some idea regarding about the atomic jumping process, right? Then in the section 2, we are going to bring some crystal lattice or different crystal structures into this diffusion phenomena. So we call diffusion in crystal lattice. In first section, in first part, we are going to introduce several atomic diffusion mechanisms in different crystal structure, included BCC, FCC. And in this part, the material we show you are metals. And in second sections, we are going to talk more about the diffusion, atomic diffusion in ionic solid materials. In this part, when we deal with the ionic solid materials, you need to consider the charge balance conditions. So you always need to make sure the total charge equals to 0, which we have a charge balance. Okay, so let's move to the first part, the thermally activated diffusion. The atoms only receive the thermal energy, so you can think about that. Yes, atoms have, due to the temperature, so the atoms have certain energy, and as long as this energy can overcome some energy barrier, then this will allow these atoms jump from location 1 to location 2, right? And what's the random walk and the correlated atomic jumping process? Based on the description, random walk means the atoms can jump here, jump layer, jump here, jump layer, so everywhere. So we call a random walk. This atom can jump anywhere he likes. So what's the correlated atomic jumping process? Correlated means what? Correlated means this jump is related with previous jump or next jump. So we call it a correlated jumping process. But random walk means that this jump is nothing related with the previous jump or next jump. So now you have some idea about the difference between random walk and correlated jumping process, right? But do you remember, as we mentioned in previous lectures, do you have any idea what type of diffusion mechanism belongs to random walk? And what type of diffusion mechanism belongs to correlated atomic jumping process? Have any idea? Random walk means the atoms can move to anywhere, right? So if you have a dope material and the dopants are located at interstitial site, when you apply, no matter it's a temperature gradient or electrical field, this interstitials moves through interstitial site. Under this situation, this kind of mechanism we can consider as a random walk because the interstitial can move to any interstitial site inside materials, right? So it's nothing related to previous work or next work. But related to correlated atomic jumping process, do you remember? Do you have any idea for that? I would say vacancy mediated diffusion belongs to correlated atomic jumping process. Why? The atoms here, right? Oh, sorry. So let me use the E. Okay. Sorry. So if you have an atom here, what's the vacancy mediated means? Means what? As long as there's a vacancy nearby these atoms, so these atoms can make a successful jump or exchange the location with this vacancy. So for sure, this is correlated atomic jumping process, right? Because as long as this atom jump here, then this jumping will affect the next jump, right? So this type of diffusion process, we call it a correlated atomic jumping process. Okay, so now you have some idea about the atomic jumping process. And just a quick reminder, don't forget, in these lectures, what we are interested in is we will try to correlate it, the diffusivity, which you can measure in macro scale, with the atomic jumping process. You can observe this in micro scale. So we will try to link these two parameters together. Okay, so this is what we are interested in. Okay, so now let's move to the thermally activated jump, the first section. So what the atoms only have the thermal energy. So what's the thermally activated jump? A series of thermally activated discrete movements or jumps between the neighboring positions of local minima energy. So this means, for example, that we have some atoms here, and the location, I have location 1 here, location 2, and location 3. And as you know, location 1 and location 2 or 3 are the lattice point. So when you try to draw the energy as a function of location x, you can observe the energy of location 1 and location 3 have a minima energy. Okay, but now we focus on the jumping process. So we focus on these atoms, these blue atoms at location 1. If this blue atom is going to move or jump to location 3, so it's going to move to location 2, then it can go to location 3. But as you know, if you really draw the materials structure, will be shown like this, right? The blue atom at location 1, if it want to move to location 2, it need to push these two atoms away, and this will cause the lattice distortion. So these atoms for sure need to have sufficient energy to push these two atoms away, then move to location 2. So based on this, you know the energy of location 2 for sure is higher than that on location 1 and location 3. And as long as the atoms move to location 2, it definitely will move to location 3 due to what? This will be belongs to spontaneous reaction because the system tend to minimize its total energy, right? So for sure, this atom is going to move from location 2 to location 3. Okay. So now, if we take a look on this energy as a function of location, we know that this difference, the energy difference between the location 2 and location 1, we call is a delta E ACT. ACT is an abbreviation of activation energy, and some people also call this activation energy as an energy barrier. So as long as the atoms at location 1 have the energy larger than this energy barrier, then it can make a successful jump from location 1 to location 2. Okay, then move to location 3 through spontaneous reaction. And this case, because it's a thermally activated jump, so the thermal energy required to overcome this energy, okay? That means the thermal energy is only source, also only energy this atom has. Okay, so this comes from the thermal energy in this case. Then we try to quantitatively describe the successful jump rate from location 1 to location 3. So we need to try to do some estimation of in the beginning, we start from in the classical mechanics. In the classical mechanics, the potential we have we have a square potential function show like this, and the atoms, blue atoms, sometimes it will stay at the E well, means at this well with the E well energy. And some atoms locate here, similar to location 2, and also the energy we call the EA. And regarding to LOL means the vibration length of these atoms inside this well, and the tau is how much time of this atom stay in this well. So we got the L well and tau well. The same idea can be performed here. LOA is the vibration length of these atoms at this state, and tau A means how much time of this atom stayed in this activated state. And the energy difference between EA and E well we call the migration energy or energy barrier. So now you have this idea, right? So as you know, the atoms usually will vibration at around its latest point, right? Always vibration. But how many atoms can make a successful jump from the well to the activated state? Do you know that? That's what we are interested in, right? So this will involve two parameters. The first one is vibration frequency, and the second one will be how many atoms have sufficient energy to overcome this energy barrier. So regarding to the how much how many atoms have sufficient energy to overcome this energy barrier will be related to with this Boltzmann distribution. This is a vertical axis. It represents the numbers of particles as a function of energy. So here we assume the energy barrier is EM. So at the temperature T1, lower temperature, we observe is a small amount of atoms can make us have sufficient energy to overcome this energy barrier. And when you try to increase the energy, increase the temperature to T2, then you can observe those more atoms have sufficient energy to overcome this energy barrier. And the probability or the portion of the atoms which have higher energy, higher than EM energy, can be predicted based on these equations will be equals to exponential minus EM divided by KT. But in classical mechanics, actually we ignore the quantum tunneling effect, which means the atom don't have chance to move to location 3 through tunneling effect. It for sure you need to overcome this energy barrier, then to move to location 2, then down to location 3. So based on this, we can write down the atomic jump rate, which means make a successful jump from here to here is equals to vibration frequency times the probability of the atoms which can cross the energy barrier. So based on this equation, we know the gamma prime, which is the atomic jump rate in specific direction. Here is along one direction. We call it a gamma prime. Equals to what? Equals to atomic vibration frequency times the probability. The probability term I just copied from this results. For the vibration frequency part, vibration frequency, so you can write down, use the velocity times the distance m. So here vibration velocity is here, and the length is the vibration length as well. So the velocity, some people probably were curious about why we can we can write express like this. You can think about that. This is just a problem, easy to remember. The energy we have is a thermal energy. You can write it as a kT, right? And third, kT serves as a is a mechanical energy. So you got mv squared is proportion with. So you just so the v will be proportion with square root of kT divided by m. kT divided by m. And why we have 2 pi is because when you derive this vibration frequency, this will involve the angular momentum. So you have a 2 pi here. And the detailed deviation, you can check the lecture note from page 40 to 41. But based on this idea, you can easy to remember the frequency part. Okay, but as we know, this is in in classical mechanics, right? This and in real in real real in real world, actually, the potential the potential well actually is not like this square potential function. It's a parabolic like. So based on this, we need to modify the in order to get the accurate atomic jump rate, we need to modify the atomic vibration frequency, and the probability is the same term, is the same, right? So regarding to vibration frequency, the results would be shown here, would be related with equals to 1 divided by 2 pi and square root of beta divided by m. Beta here actually is a false constant, and in materials, we consider this is related to bond strength between atoms. And m is a mass, but here is a reduced mass related to the atoms we're talking about, what type of atom we're talking about. So how to get this atomic vibration frequency in quantum mechanics? So we are going to use we call the harmonic oscillation model. So by using this harmonic oscillation model, you can get this atomic vibration frequency. So let's give you a quick review related to talk about what's the harmonic oscillation model. This model actually is very different with the one we learn in classical mechanics. Because in classical mechanics, we think the atoms just move, nothing related to other atoms. Each atom is independent. So it can make an independent movement. But in the quantum mechanics or harmonic oscillation model, actually we consider there's a the two atoms were attached together by a spring. You can consider a spring. So the behavior will be like this. So when you try to write down the force between these atoms, then you can get these equations. So by solving these equations, you can calculate the vibration frequency of these atoms expressed like this. And the K here actually is a spring, so we call the force constant of this spring is a K. But here, this is atom 1 and atom 2, so there's a bond in between, right? So this force constant is related to the bond stiffness or bond strength. And the mass here is a reduced mass, is related to this atom 1 and atom 2. So we use a reduced mass to substitute it. So based on this, if you know this, so let's back to the the atomic jump array gamma prong in quantum mechanics will be expressed like this vibration term and the explanation term. So here we know when you talk about the atomic jump array in real world, we know that it will be affected by the bond strength, and the bond strength is related to what is a covalent bond, metal bond, ionic bond, right? So it will be related to materials, and the mass will be related to what type of atoms you choose. And also the second term is related to the environment temperature and also the energy barrier. Okay, so this will affect the atomic jump array, which means the material structures for sure will affect the atomic jump array and further affect the diversity of this material. Okay, so let's take a close look in atomic jumping process in materials. And also don't forget, do you have any idea about the relationship between the diffusion and atomic jumping process? Diffusion is a result of a series of discrete jumps. So what this means means that if the atoms, the blue atoms, start from here, before diffusion, it stay here, and when diffusion happens, which means this atom is going to make a jump, we call it a small r vector of small r1, and r2, r3, and after time tau, this atom is going to dun, 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 to arrive this location, and we have capital R represent the displacement, the total displacement after n tau times jump, or after time tau, right? So now we need to define some terms. Total jumps during this diffusion. Total numbers of jump n tau equals to gamma is a jump array times time tau. So this jump array, total jump array, is a gamma instead of gamma prime. In previous slide, we use gamma prime. We point out this is the jump array along one direction. But here, because you cannot consider, you need to consider all possible jump directions here. So we call it as a total jump array, included all possible directions, and times the tau, so you got the total jump numbers. Okay, then displacement of each jump. So it's a small r. We have r1, r2, small r1, r2, and r3 is each jump. That is a displacement of each jump. It's a vector. And we also have capital R. Capital R is a displacement after n tau times jump, or after time tau, right? So just summation O vector of small r from I equals to 1 to n tau, then you got the capital R, which means the displacement after diffusion. Okay, so now you have some idea about the atomic jump array, and you also know diffusion for sure is a result of series of discrete jumps. But don't forget, our purpose here is we try to find an indicator, or try to find a relationship between the diffusion and atomic jump, right? So we try to find an indicator to describe the diffusion phenomena, and this indicator not only can describe the diffusion phenomena, it also can relate it with atomic jump. This is what we are interested in. So let's give you an example here. Some people probably will say, oh, professor, why don't we use the capital R, this vector of capital R, to correlate the diffusion and atomic jump, because it had shown this relationship for sure, right? It has summation of each jumps. So is capital R, vector of capital R can be an indicator to describe the diffusion phenomena. So let's take a look on this slide. So before diffusion, we have a point source at the center. And when diffusion happens, you can observe these blue atoms jump outside and jump more, diffuse out, spread out, right? So after time tau, if you try to use the vector of capital R, then we will say, oh, it can summation of each jump, right? But this is a random walk. So if you summation all the small r together, then what's the capital R? Vector of capital R is the total displacement of this atom will be equals to, because it's random walk. So when you try to summation the vector of small r will be equals to 0. So this result show you that if you try to use the capital R, this displacement after diffusion, to describe the diffusion phenomena, you cannot do that because your samples did diffuse, the diffusion did happens, but the capital R equals to 0, right? So it is not a good indicator to describe the diffusion phenomena. The ideal indicator would be what? The ideal indicator means that when diffusion happens, it will be have a proportional relationship, right? The indicator, when the indicator increase, then the diffusion will increase. Some is a proportional relationship. That one will be a good indicator. But the capital R is not a good indicator for sure, right? So our textbook introduces you the other parameters to hope that one can be a good indicator to describe the diffusion phenomena and also can correlate with the atomic jumping process. So what this is will be here. We introduce you two terms. The first one is the average displacement. You just consider the average all capital R together, so you got the average displacement. This one is also a vector. So random walk, if you deal with the vectors, the results in both of cases will equals to 0. So the textbook introduces you the other choice. Or the other candidate would be we call a mean square displacement. Mean square displacement means you dot two vectors of R together and take the average on each atoms. So each capital R, then you will got the scalar. You got the mean square displacement, right? Okay, so based on this, let's take a look if you try to dot to capital R, then what's the results here? So do you remember what's the capital R? It's a summation of small r, right? So if I try to, for example, like if you capital R is a small r1 plus small r2 plus small r3. So so you got r1 plus r2, right? But this is vector, don't forget it's a vector. And you dot with also r1 and r2. And also R3, R4, just take this example. So you will get R1 times R1, R1 times R2, right? R1 times R1 plus R1 times R2, R2 times R1, and also plus R2 times R2. So it's what this means. So after organize this, you will you can get you can get this, right? You can get the R1 dot R1, R2 got R2, R3 got R3, so you got the first term summation Ri squared, and I started from 1 to n tau. And the rest of part you got R1 dot R2 and R2 dot R1, so you can put the 2 in front of it and summation Ri dot Ri plus j, and I equals to 1, j equals to 1, so you got R1 dot R2 plus R2 dot R3, and you got a 2 here. So we successfully to get this equals to this, right? And don't forget the diffusion involves many atoms, right? Many atoms do the diffusion process. So we need to average all numbers of independent works of trials for all atoms. So we take the average on these equations. So what we get here, we average this term, so we got the average. This is the mean square displacement. And we also average this term, and we average this term. So what we have here, if you try to average this term, you just divide it by the numbers, total jump numbers. So you got divided by n tau, and you got the mean square jump distance. So if this one will equals to n tau times mean square jump distance here, and this one just average it. So we put the average sign symbol here, and Ri dot Ri plus j. So we got Ri times Ri plus j times cosine theta is the angle between I and j, vector Ri and vector of Ri plus j. Okay, so let's take a look on to answer whether this mean square displacement can be a good indicator to describe the phenomena, the diffusion phenomena, also link with the atomic jumping process. So let's take a look. So based on our deviation, we find that mean square displacement, the n tau is related to total jump number, is a jumping numbers, right? So when diffusion time increase, means the jumping numbers increase in the meantime. So yes, it can well describe the diffusion phenomena in macro scale, right? And also it will related to mean square jump distance. What the mean square jump distance means? It is describe the atoms, the average jump distance of these atoms. So it will directly, this is related to a crystal structure. FCC-BCC will related to, because make a successful jump will be related to lattice constant, right? And also the mechanism is you jump from one lattice point to the other lattice point, or you jump from interstitial side to the other interstitial side. So this will be related to the crystal structure and also diffusion mechanism. And also, based on these results, this mean square displacement successfully to link with diffusion phenomena and also the atomic jumping process. And regarding to the second term, is a summation of cosine term. If the jumping process we talk about is a random walk, for sure, summation of cosine term will becomes to 0. So if it is a random walk, the mean square displacement directly equals to this value. But if it is not a random walk, you need to consider this term. Okay?